All right, so in the previous couple videos, we talked about how to calculate the instantaneous rate of change. So we're going to take that a little bit step further, and right now we're actually going to determine how we figure out a function which gives us the instantaneous rate of change at any point on a curve. And what this function is called is the derivative, okay? So again, remember that when we're talking about rates of change, we're really talking about slope. Okay, and what we found out in the last couple videos was that instantaneous rate of change means instantaneous slope, which we know as the slope of the tangent line to a curve at a specific point. Now in the previous videos we calculated what that slope was and got a number like 5, -4, 700 million, okay? But what we do when we calculate a derivative is we're actually finding a function which if we input a value say x, t, any other kind of independent variable, it will spit out what our instantaneous rate of change or what the slope of our tangent line to that curve is at any point we desire, okay? So there are many different ways we use, or many different symbols I would say, we use to describe derivatives. All of these symbols mean the exact same thing. We've seen a couple of these before. Remember, we had looked at dy over dx and df over dx. Remember, what does that d mean? It means infinitely small. So what both of those two terms mean is infinitely small rise over infinitely small run, okay? You really got to remember that because it's very important to understand what that d means, okay? Now, when we see it in this form right here, when we have d over dx and then something in parentheses, that means do the derivative operation or calculate the derivative of the function f of x, okay? Now another way we describe derivatives is using this prime notation here and here. So if you see a variable with a prime over it, that also means the derivative. This case, f prime of x, that means the derivative of the function f of x. Y prime means the derivative of the line y. Okay, so all of these things mean the exact same thing, and we're going to be using all of these symbols for the derivative over and over and over again throughout the course of the year. So even though there's lots to remember, trust me, it won't be that hard. Once we get into them, you'll always associate these things with derivatives. So the way we calculate the derivative is through this equation right here. This equation is called the difference quotient. And what you might realize, difference wow, that was painfully long to write. And I'm not 100% positive that I spelled difference right. But you know what? This is a math class, so who cares? Okay. Anyway, so you'll notice that what we had before when we calculated the instantaneous rate of change, instead of an x here, we had an a at these 2 points. All right. So now that we have an x, what we're going to get out is when we evaluate this limit, we're going to get a function of x instead of some specific number. Okay, because that's what we're looking for. That's what the derivative is. It's a function. All right, so let's look at a couple examples of how we'll actually calculate derivatives. All right, so in this case, we have a function, f of x is equal to 2, and I want to know what is f prime of x, meaning what's the derivative. Again, remember that the derivative is a function that will tell us the slope of the line tangent to the curve or the instantaneous rate of change of that function at any point along that function. So what I'm going to tell you right now is that given this function right here, you can actually tell me what f prime of x or what the derivative is without doing any math whatsoever. Okay, let's see how we can do that. If we graph f of x, x equals 2, or y equals 2, that's just going to look like that. It's going to look like a horizontal line. Now, what's the slope of the line tangent to this curve right here at any point? Anyone? Bueller? It's 0, okay? So the derivative of this would be 0, and this gets us to a very important point, which is that the derivative of any constant is always equal to 0. However, if we wanted to go through our difference quotient and solve for this, we would plug it in like so. Because our function is not a function, it's written as f of x, but really it's not a function of x. It doesn't matter what x is, it's always going to be equal to 2. When we do f of x plus h minus f of x, we're always going to get 2 minus 2, which is always going to give us 0. So therefore, the derivative is 0. Okay? Now, one important thing we get from this is that the derivative of a constant is always equal to 0. Okay? That's going to be something that you guys are just going to have to commit to memory, and it's going to make solving derivatives really easy if you remember things like that. Okay? So let's move on to the next example. Now, here's another example that I'm going to say, again, just like the last one, you guys can actually tell me what the derivative f prime of x is without doing any math whatsoever. Look at what we did in the previous example and see if you can figure out what we got to do. Pause the video and try to figure it out for yourself. All right, so hopefully if you remembered that, again, a derivative is a function that gives us what? It gives us a function that tells us the instantaneous rate of change at any point or the slope of the line tangent to the curve at any point. So if we plot the line 2x plus 1, that looks something like that. The slope is 2. So therefore, what is going to be the slope of a line tangent to this curve right here at any point? Well, the slope is always going to be 2. So in this case, our derivative is just going to be 2. Okay? Now, if you don't believe me, well, let's go through the difference quotient and actually calculate it out using math, Mr. or Mrs. Smarty Pants. All right. So if we do that, if we plug this into our difference quotient, we're going to get this. Now, if you go through and simplify this, distribute that 2 up there, we're going to get this guy. So what kind of magic do we see happening right here? Well, we have a 2x right here and a negative 2x, so those are going to cancel. We have a 1 and a negative 1, so those are going to cancel. And what we're going to be left with is just this. We're going to get, whoops, we're going to end up with 2h over h, which, what can we do to this? Well, if we have an h in the top and an h in the bottom, those can cancel, and we're just left with 2. So, yeah, we were right. Okay, we didn't need to use any math to figure this one out.